All right, here we are. We're looking at lesson 18, specifically on page 239. We're starting off with a summary, and we're trying to work with solving for logarithmic equations. So thus far, we've been seeing that logarithmic equations answer exponential knowns. So one way that we can work with dealing with logarithmic equations is by taking the logarithm, like log base b of the argument y equals L, and translating it into an exponential equation and then solving from there. So for example, if we have a logarithm with a base of 2, an argument of 1 minus x is equal to 4, what we're going to do is we're going to take the base and the answer to the logarithm, and then we're going to translate those into an exponential equation. Base of 2, exponent of 4. Again, what I just did here, y'all, is I took these two things, 2 and 4, and turned into 2 to the 4th power. And then what that's equal to is the argument. So I dropped the argument 1 minus x down right over there. So nice. So now we are here. What I'm about to highlight in purple, we're here. That 2 to the 4th is equal to 1 minus x. From here, we can solve it down, evaluating 2 to the 4th to be 16. And then isolating x by subtracting 1 on both sides to give us 15. And then dividing both sides by -1 to get x by itself, getting our answer that x is equal to -15. Put a box around that, or circle. Cool. Another thing that we could do is if you have logarithms with the same base, log base b and log base b, you just set the arguments equal to one another, x and y equal to one another. This follows a lot of logic that we've been doing with exponential equations in last unit and rational equations the module before. So in this example, notice both of these logs are common logs, log base 10. So really what we're doing here in this problem is we are now setting the arguments equal to each other and solving. Cool, x equals 3. Now, I was asked a question, a really good question about extraneous solutions. Extraneous solutions are answers that make your original equation untrue. We saw this in the case of rational, aka fraction functions, two modules ago. They were values that made the denominator equal to 0, made the denominator impossible. We know we can't divide by 0. So therefore, if we have an answer that plugs back into our original logarithmic equation and it makes an impossible statement, an impossible solution when checked, that would be extraneous. And again, we built that idea of extraneous off of extra or not usable, impossible.